Today we are looking at activity 23, which we're talking about modeling with exponential functions. So we have both compound interest type problems, population growth problems, and just being able to create our own exponential function from the data. So you can see our three different goals here for this lesson. The first one, where we are going to create an exponential function to fit data, uses our Desmos calculator. So I taught you in a previous lesson how to do linear regression in Desmos. So we're just going to do a real quick, very brief review of that. If you need to go back, within the Google Classroom or back to old videos to catch and look at more details for doing that, you can. But first thing we're going to do when we use Desmos to type a table in. So I've got the OST version of Desmos here up. In order to do a table, you click on the plus sign to add item, and you click on table, and then that's going to give you the option to add in all of the numbers that you have. So looking at the table that is in our notes here, I'm just going to type in all the x's and all the y's exactly like I see them. So my x1 is 0. If you press tab, it'll automatically go to the next cell. So then 3 for the y, then press tab again, it'll go down to the next one. And so then we can just continue on our merry way of entering these various values. So 3 and 10.125. All right, so there is our table. And once we have the table, that doesn't really show anything on our graph other than just the plotted points. It doesn't, show us any type of connection or any of that. So the next thing that I had taught you when we originally did linear regression was how to actually have it calculate for you the line of best fit, and that's why it was called linear regression. So what you actually type in to Desmos is exactly this: y1, and then this is called a tilde. It's above, like usually in the top left-hand corner of your keyboard, and then you type mx1 plus b. So it's really important that you remember to put the y1 and the x1 and not just y and x. If you just put y and x, you're going to get an error message. But the reason we're doing x1 and y1 is because that's the values that are actually in this table. So we do y1, and all you have to do is type y and then 1. It automatically makes it the subscript for you. So then press shift and hold down the key to get the tilde. And then we do m, x, and then again, just type the 1 right after. It'll automatically make it a subscript. Then hit shift to get the plus sign, and then b. And then it should give you exactly what you see here. It gives you a value for m, a value for b. So it's saying, hey, the line of best fit here for these points has a slope of about 2.36 and a y-intercept at about 2.55. Remember that we talked about R as showing the strength of the linear correlation. So notice that they've also graphed that line of best fit for you so that you can see it. So that information right there is exactly what is screenshotted onto your notes here, so that you could follow along and see everything that was in there. Again, when we are looking at correlation, we're looking at the R value. Since R here is 9.845, that shows a very strong positive correlation, which would lead us to say, oh, yes, this is linear. But that's why that's not the only thing that we look at. When you look more closely at the points in comparison to the line, we don't have any points that are actually on the line. The y-intercept is above the line. The last point is above the line. The other 2 points are below the line. So when you don't have any points on the line and you have like, you know, an over, under kind of development there, that's a telltale sign that the data may not actually be linear. So typically when we're looking at something like this, we'd want to have a lot more than 4 points to make a decision. But what we're going to do now is run what's called an exponential regression and see if that gives us a better fit where we actually end up with some points on the line instead of everything being above and below. So exponential regression is the exact same thing as what we just did, except it's instead of y equals mx plus b being what we're basing it off of, we're basing it off of the exponential function y equals a times b to the x. So of course, we make our y into y1 and our x into an x1 here. So all we're going to do is go now to this and change it. So y1 tilde a, and then you don't have to type times because if you put b right next to it, it automatically does multiplication. Then you're going to need to click on the caret button, which is Shift 6, and then you'll type x1 up there. So when we do that, notice that it shows us an exponential function of best fit. It shows us an r² value, and it also gives us the values of a and b. Remember that a tends to be our initial amount, b tends to be the change factor when we're talking about an exponential function. So when we look back now at this data, so this is the same thing that you saw on my Desmos calculator. So what do you notice about the new graph? So I want you to take a look at this, compare it to what we saw here, and go ahead and choose what you think is the most important thing to notice about this new graph. All right, hopefully you said, why is it not giving me the color I wanted here? There we go. The exponential equation goes through all of the points. So the line didn't go through any of them. This goes through all of them, which means that this is a perfect fit. This isn't just the equation of best fit, this is the equation because it touches all of the points. So we ran an exponential regression with our Desmos calculator. It was a perfect fit. The other way that we can tell whether something is a perfect fit or not with exponential regression, or even just if it's a good fit and not necessarily a perfect fit, is based on the r² value. So with linear regression, we looked at the r value. With exponential, we're going to look at r². So the closer r² is to 1, the better and more accurate that model is. So in this case, because you can see here, A and B, our A goes here, our B goes here. A is my initial amount of 3, B is my change factor of 1.5. So that would be our equation in this case. Exponential functions occur in many different places. Compound interest, population growth, population decrease, radioactive decay, all kinds of things. So hopefully you've heard the term interest before, which is, interest is basically the cost of money. So if you borrow money, you have to pay to borrow it. So you're paying someone or some institution interest if you borrow it, which most people have to do at some point on big purchases, especially like a car or a house. If you lend money or deposit money into an account that gives interest, you're going to get paid that amount. So interest is good when you have money. If you're earning interest, that's good. If you are the borrower, not so good for the interest because it can be really expensive if you're really borrowing more than you can afford. So, credit cards. If no one has told you that credit card debt is bad, then you are learning that lesson right now. Credit cards charge an interest rate of about 15%. That is a lot because interest is exponential. You saw when we did the sequences and when we did the functions, how quickly these exponential functions take off. When you have a large interest percentage, it takes off really quickly. So when you are using a credit card to buy something, even that's a small cost, if you don't pay it off, you are going to end up paying so much more than what the item actually cost. So, word to the wise, don't put anything on a credit card that you can't afford to pay off at the end of that month. So, compound interest is the interest you pay upon the interest. And we have a formula to calculate compound interest. And in this compound interest formula, every letter stands for something. So in this case, A is our final amount. So how much total money do you end up with? P stands for principal, which is the initial amount. R is the interest rate. What's really important here is that it has to be the interest rate as a decimal. Has to be as a decimal. N is the, and this is N2 obviously, number of times compounded, compound interest. And then T is the amount of time. Usually this is number of years. In some cases it might be number of months or something like this, but usually this is number of years. So for the number of times compounded, here are your hints. If it says compounded daily, then N is 365. So common compounding terms means what does your N equal? So daily, N is 365. Monthly, N would be 12. Quarterly means 4 times a year, so N is 4. Semi-annually means twice a year, and annually means once a year. So all that information is going to allow us to solve this problem in example 1. Your credit card charges an interest rate of 15% compounded daily. You buy a 77-inch flat screen TV for $3,500 and you forget to pay your credit card bill for 6 months. How much will you owe in 6 months' time? So I definitely don't recommend actually doing this in real life, but we're going to figure out what that would cost you. So final amount is what we're trying to find. So A equals P, principal, the initial amount. So that's the initial amount that we charged, which I want you to go ahead and type in. So what is the initial amount? What should we be plugging in for P in this situation? All right, hopefully you said 3,500 because that's the initial amount that we charged. Next, we do parentheses 1 plus R is the interest rate, but as a decimal. 15% as a decimal is 0.15. So we move the decimal, always 2 places left to make a percent into a decimal, 2 places right if we're going the opposite direction. So 0.15 is my R, divided by N. So it says compounded daily, so that means N is 365, raised to the NT, so that means N times T. So we already know N is 365. And then time. We said time is typically number of years. So in this case, we're talking about 6 months. Don't put 6 here because we're going to not be having a whole year. 6 months is half of a year, or 0.5. Since it's a real life situation, you're allowed to use the decimal if you want as well. So now we're going to go ahead and enter this all into our calculator. I keep giving plugs for the reason why you need to have your own handheld calculator, because when we get to problems like this, knowing how to use a calculator that is in front of you is really important. And yes, you can get the Desmos to do some things, but I'm telling you that it's not going to do this as nicely. This, I can actually type it all in on either a TI 83 or 84 or a TI 30. I can type it all in just as we see it. So I can do 3,500, then parenthesis, 1 plus, and then my fraction button, alpha y equals, choice 1, and I can type in my numerator as 0.15, scroll down, make my denominator 365, scroll right to get out of that, close the parenthesis, then use my exponent button and do 365 times, I'll use 0.5 this time because it's easier than using the fraction button. Now I've got everything entered exactly as I had it here. So go ahead and press your enter button and we get $3,772.54. So $3,772.54. Notice how I rounded. Unless it tells you otherwise, if we are talking about money and the answer is money, you should round to the nearest cent. If it specifically says round to the nearest $1,000 or to the nearest dollar, then obviously follow the directions. But in this case, it doesn't specify, so we round to the nearest cent. So in just 6 months, look at how much more you've paid, $272 more just for the fact that you have to pay the interest. All right. Example 2, an invasive species of carp was introduced into the Mississippi River in the 1990s. These fish are overtaking the rivers and threatening the Great Lakes fishing industry. Use the graph below to answer the questions that follow. So now here we're using a graph to talk about population in context. So the in context part is the important part. So it says, what does the y-intercept represent in context? So notice it doesn't say what is the y-intercept. Now if it did, hopefully you would all tell me 0, 20 is my y-intercept. But in context, we're putting labels. Remember that when you are interpreting a point in a real life situation, you have to talk about both the x-coordinate and the y-coordinate. So x is 0 in this case, and because x stands for years since 1990, when x is 0, that means in 1990. That's what this 0 part means. Now we look at the y part. It says 20, and our y stands for number of carp in thousands. So we would say there were 20,000. Don't just say 20, 20,000 carp. Part B, estimate the number of carp in the river in 2010. So you guys are going to do this one. First thing you need to do, just to give you a little hint, you're not looking for 2010 on this axis. This is years since 1990. So your first step is to figure out how many years since 1990 2010 was. Then find that on your axis. So you're going to estimate the number of carp in the river in the year 2010. Okay, so first thing we do is say 2010 minus 1990, or you can just do it in your head. You don't have to actually subtract. You could say, okay, 10 years to the year 2000, 10 more years to 2010. So it's 20 years is my x. So I go over to where x is 20, and I go up to find that point on my actual graph, and then I go over on the scale. So we're counting by hundreds here, and 150 would be the halfway mark. So it's definitely more than a quarter of the way. It looks like it's maybe about a third of the way between 100 and 200. So because it says estimate, there are lots of correct answers that I would accept here. But I would definitely use the approximate symbol when you give your answer. It does for sure need to be less than 150,000, but more than, say, 125,000. So I'm just going to guess about 135,000 carp. But again, if you guesstimated 130,000 or 140,000 or 142,000, those would all be considered correct because of their closeness on that scale. All right. Last one here, the equation of the graph is y equals 20 times 1.1 to the x, where y is the number of carp and x is the year since 1990. What is the rate of growth as a percentage? So, the way that we find this is by looking at the growth factor. So, you should know from our previous lessons that the B value is your growth factor. So, because that is 1.1, what that means is that we have 110% of what we started with, because 1.1 as a percentage is 110%. Now, that's not the answer. Just because it says percentage and this says percentage doesn't make it the answer. The answer is the difference between this and 100%. So, because it's asking the rate of growth, well, we started at 100%, so the growth was 10%. So in this case, from this equation, we could tell that the rate of growth is 10%. All right, hopefully that all makes sense. If you have questions, please reach out. Otherwise, you are ready to go to start your practice problems.